Okay, so in this video, I wanted just to go through dipole-dipole forces. Now, in the previous video, we spoke about van der Waals forces, saying they were a type of intermolecular force. Well, dipole-dipole forces are another type of intermolecular force. So remember now what that means. Inter, think of all the E's. Inter means that these are forces between atoms or between molecules, one molecule and the next, okay? Now, dipole-dipole forces occur between polar molecules. So like, do you remember in the previous video on van der Waals, we would have said that van der Waals forces arise between non-polar molecules, okay? These are between polar molecules. So for example, HCl. Now, if you look up the difference in electronegativity between hydrogen and chlorine, you'll see that it's greater than 0.4 but less than 1.7. So that's our rule for a polar bond. And the chlorine is slightly negative because the chlorine is more electronegative and will pull the electrons closer to it, making the hydrogen then slightly positive. So in a neighbouring HCl molecule then, you're going to have the same thing. You're going to have the hydrogen slightly positive, the chlorine slightly negative. These are permanent dipoles now. Now, just to remember again, what's a dipole? So a dipole is where you have a region of positive and a region of negative charge separated by some distance. But this time, these aren't changing. These are permanent. They're always. Chlorine is always slightly negative. The hydrogen is always slightly positive. So there isn't a change in the dipole. And the type of intermolecular force then that you have between one polar molecule and the next polar molecule, dipole-dipole forces. Dipole-dipole forces are a bit stronger than van der Waals. So that would mean that something like HCl would have a much higher boiling point than something like neon, something that has van der Waals forces between the molecules. So the dipole-dipole force is stronger than van der Waals, so these molecules would have higher boiling points, much higher boiling points, okay? The other thing to bear in mind is that the greater the electronegativity difference between the elements, then the greater the permanent dipole will be, and therefore the stronger the dipole-dipole interaction will be, okay? So the bigger the difference. So you look up, when you look up the values for hydrogen and chlorine, if you've got a much bigger electronegativity difference closer to the 1.7 range, then that will mean that the dipole is much stronger or greater, and therefore the dipole-dipole force between the molecules will also be much stronger, okay? Now, the last type then of intermolecular force that we need to talk about are called hydrogen bonds. Now, hydrogen bonds are a special type of dipole-dipole interaction. So again, hydrogen bonds occur between polar molecules because they're a type of dipole-dipole interaction. But they'll only, because look, hydrogen's in the name, so hydrogen has to be bonded to either fluorine, oxygen, or nitrogen. Now in class I would sometimes say, try to remember phone. So, where you're F-O-N, phone, that will hopefully help you to remember the elements that nitrogen has to be bonded to. The reason it's hydrogen bonded to fluorine, oxygen, and nitrogen is because they're the most electronegative elements that you'd have. So these would have quite significant difference in electronegativity between hydrogen and fluorine, between hydrogen and oxygen, and between hydrogen and nitrogen. So these give rise to quite strong intermolecular forces as a result, the hydrogen bonds. Now, something like HF, so look, you have hydrogen bonded to fluorine. So if you saw HF, and say I'll draw 3 molecules of HF, the intermolecular bonds there are fluorine is more electronegative than hydrogen, so it's slightly positive. Fluorine is slightly negative, and the hydrogens are slightly positive. So these are the hydrogen bonds there that you have between one HF molecule and the next and the next. Hydrogen bonds stronger than dipole-dipole forces, and therefore HF would have higher boiling points than the ones that have the molecules that have dipole-dipole forces between them, okay? Water is the most common one where hydrogen is bonded to oxygen. Okay, so that's one water molecule. If I draw another water molecule, now oxygen is slightly negative, the hydrogens are slightly positive. So you have, look, hydrogen bonds between. Okay, now if you had another water molecule down here, look, You can have hydrogen bonding there too. So you can have 2 hydrogen bonds per molecule of water, okay? So that's why HF has a greater difference. There's a greater difference in electronegativity between hydrogen and fluorine than there is between hydrogen and oxygen. But actually oxygen has a higher boiling point because you have more hydrogen bonds to break. So even though the difference in electronegativity is greater between H and F, you'd expect these hydrogen bonds to be greater as a result because this is a stronger permanent dipole. But because you have 2 hydrogen bonds per molecule of water, water actually has a higher boiling point. Ammonia then, NH3, look, where hydrogen is bonded to nitrogen. Okay, so NH3, and then the hydrogen is slightly negative. Sorry, the nitrogen is slightly negative. The hydrogen is slightly positive. And if you had a neighbouring ammonia molecule, then, okay, you'll have hydrogen bonds between one ammonia and the next ammonia, and remember they're quite strong. Okay, now in terms of the organic course, then you need to try and remember I said to you in the previous video for van der Waals, I would have said that van der Waals forces occur between alkanes, alkenes and alkynes because they're not polar. You need to try and remember that aldehydes, ketones and esters, they all have polar bonds, okay? So they can have dipole-dipole forces between the molecules. So if I draw an aldehyde, say, so remember the functional group for the aldehyde was the C double bond O and a H, okay? So there's the functional group. Now, this is a polar bond here. When you look up the difference between carbon and oxygen, it's greater than 0.4. C and H, no, non-polar, but this is a polar bond. So if you have a neighbouring ethanol, what types of interaction can you have? Oh, sorry, 1 second, I'll rub that out. So that's a H here, so polar bonds, what I've written there, and that's slightly positive here. So look, you could have an interaction between the slightly negative oxygen of one aldehyde and the slightly positive carbon of the other aldehyde. They would be dipole-dipole forces now because this is a permanent dipole here. Permanent dipole, okay? So similarly, if I drew something like this is propanone, isn't it? So CH3 and 1, 2, 3. So propanone, remember the ketone functional group? That is also a polar bond, okay? So if you had a second molecule of propanone here, okay, that's a carbon there, okay? So if you have, so remember, you must identify, you see, is there a polar bond or not? There is a polar bond there. So again, dipole-dipole forces. So if you're asked in an exam question, account for the difference in boiling point between methane and methanol, okay? Then you'll have to talk about methane having van der Waals forces between the molecules. Aldehydes like methanol has dipole-dipole, and because dipole-dipole forces are stronger, then the aldehyde will require more energy to break those bonds and to separate the molecules into gases, to make them gases. So aldehydes, ketones and esters, because they have a polar bond, those molecules can have dipole-dipole forces between them, and that will give rise to higher boiling points because the dipole-dipole forces are stronger than the van der Waals that you'd have between alkanes, alkenes and alkynes. Now bear in mind that you must sort of compare corresponding ones. So like methane, the corresponding aldehyde would be methanal. If it was propane, the corresponding aldehyde would be propanol. You have to stick with the same number of carbons. Otherwise, you see, you'd be comparing molecules that are much bigger than others, and you can't do that because another factor that determines boiling point is the size of the molecules. Heavier molecules have higher boiling points. So like you must compare like with like, if you like, so similar numbers of carbons. Okay. Finally then, in terms of organic, you're going to be looking at the alcohols and the carboxylic acids as homologous series that can actually have hydrogen bonding. Okay, so there's hydrogen bonding between. So if I drew ethanol here, okay, so remember the functional group of the alcohol was the OH. I'll actually just extend the OH out there. And then if I have a neighbouring molecule here of ethanol, H and H, Okay, so second now, it's a bit messy looking. So that's a HOH here. So the functional group of the alcohol here and here is a polar bond. Slightly negative oxygen, slightly positive hydrogen, okay? So you can have interaction there, look, between that alcohol and the next alcohol. All right? So hydrogen bonding, why can you have hydrogen bonding between alcohols? Because you have hydrogen bonded to oxygen. All right, and similarly, the functional group of carboxylic acids, OH. Now look, you actually, so that's ethanoic acid I'm drawing there. You actually have two polar bonds there. So if you drew a corresponding, another molecule of ethanoic acid here, you can actually have, that's slightly positive, slightly negative. This is slightly positive, slightly negative. Look, you can actually have two hydrogen bonds per molecule. So with alcohols, you could only have one hydrogen bond per molecule, but with acid you can have two, so they're called dimers. So as a result of that, you have twice the number of hydrogen bonds between acids than you have between alcohols. So acids would have higher boiling points than corresponding alcohols. Okay, now there's two properties they're going to ask you about. So the first property there we've spoken about is the boiling point. So in exam questions now, they'll ask you to account for or explain the difference in boiling points. So you'll have to think about the size of the molecule, remember, the MR, the size, but normally the size is around the same. And then they'll say to you, what else would make a difference in terms of boiling point. So you'll have to talk about intermolecular forces then, okay? And remember that van der Waals are the weakest, dipole, and then hydrogen. So if it was organic, you'd be saying, well, the lowest boiling point, the families with the lowest boiling points would be alkanes, alkenes, and alkynes. Then the next lot would be the aldehydes, the ketones, and the esters, because they have dipole. And finally, then you have alcohols, and the highest boiling points would be belong to the acids, because they can have dimers, remember, between the molecules, okay? Now, the other property that you need to talk about is solubility. Now, solubility from second year, you'll remember it means does a substance dissolve in a solvent or not. The substance is the solute, the solvent is the water. Now, we're going to use a sentence like dissolves like to help us, okay? So you just need to focus on the exam questions and say to yourself, is this non-polar substance or solute, or is it a polar substance or solute, okay? If it's non-polar, it will not dissolve in a polar solvent like water. It will need something like cyclohexane, okay? So like dissolves like. So non-polar solutes dissolve in non-polar solvents. If it is polar substance, yes, it will dissolve in water, because water is our most common polar solvent. So remember, look at water, look at the difference in electronegativity. There are permanent poles of negative and positive charge, dipoles there. So that's a polar solvent. So what would dissolve in water? Polar substances and ionic substances as well, because they have charges. So the slightly positive hydrogen of the water will attract the slightly negative sodium ions. The negative oxygens will attract, the wrong way around, of course. The negative, unlike charges, attract, don't they? So the positive hydrogens attract to the negative chlorines, that's what I should be saying, and the negative oxygens would attract the positive sodium and break up your ionic substance, okay? If it's a non-polar substance like iodine or something, will not dissolve in water. That will require cyclohexane. Now, how did I know iodine was not polar? Well, it's I2. You don't even need to look up your electronegativity values there now, because they've the same atom. They must have the same value, so the difference is 0, okay? Methane, any of those, the alkane, the hydrocarbons, methane, ethane, alkynes, they also are non-polar, so they don't dissolve in polar solvents like water. They would require non-polar solvents like